Hello, and welcome to another episode of The Message from Deep Space. I'm Alex Rose, aka Safety Dad, and we are on episode 18, and we have just gone through some basic chemistry. So last time we learned about combining molecules and them splitting apart, and so how to make a reaction, and then how we define a... So reaction is an action, and then also a recipe to define a saved set of reactions that we can reference later. Now, here we've got 3 new words. So, we're being told that we're going to talk about these 3 new words. Then, these 3 new words make an atom. So, if you are familiar with particle physics at all, you'll know that atoms are made of, classically, electrons, protons, and neutrons. So, we don't know which of which is what yet. So, we're going to say particle X, particle Y, and particle Z. Okay, so now particle X and particle Y and particle Z are smaller than an atom. So this is true because they're all composite elements of an atom. Now, maybe we can get some information about what differentiates what. So one particle X and one particle Z make atom 1. So this is going to be proton and electron, but we don't know in what order yet. So that does make particle Y a neutron. Neutrons, the neutral particle, like Bautista. Exactly. Okay, so now one particle X and one neutron and one particle Z also make atom 1, which can be true. You can have a hydrogen isotope that contains a neutron. One particle X, 2 neutron, 1 particle Z also makes atom 1. 2 particle X, 1 neutron, 2 particle Z makes atom 2. This is helium. That is correct. 2 particle X, 2 neutrons, and 2 particle Z also make helium. So 6 particle X, 6 neutrons, 6 particle Z makes atom 6. So it's not going to be up until we get past the second valence shell, I think, where it's going to start mattering. The difference between electrons and protons. Well, not that it's going to start mattering, but that we'll be able to tell the difference. So particle Z is smaller than particle X, therefore particle X something, not particle Z. Okay, well, the fact that particle Z is smaller than particle X means that we can safely define that as an electron, and this as a proton. Electrons, the smallest thing we've defined so far. And it still takes up frequency just like every other word. What does that mean? Not sure. I thought it sounded poetic. Maybe I should be a poet. Do not quit your day job. This is my day job. Alright. And protons. Woo! Protons! I hope you're right. I also hope I'm right. Protons, neutrons, and electrons. We've got them all! Now it makes sense why the 3 were all defined in a single transmission. They were defining subatomic particles. It's all making sense for now. For now, let's continue. Okay, an electron is smaller than a proton. Therefore, a proton is something not electron. I don't actually know what they're asking. Maybe equals? Yeah, because I guess they're oppositely charged. I was good at what I did at the observatory at grad school. Yep, I'm not one to brag, turning a new leaf. But I was pretty great, actually. It wasn't just grunt work I did. I picked up on patterns. The younger a nebula, the higher its metallicity. It measures the ratio of hydrogen and helium paired to every other element. Metals to nonmetals. That's what us astronomers care about when it comes to atoms. We keep it simple. If it ain't hydrogen or helium, it's a metal to us. Drives chemists nuts. So a higher metallicity Means less hydrogen and helium and more other elements? Right on. And hydrogen and helium are the elements with the lowest mass, which means a higher metallicity means a higher density. So it postulated that a higher metallicity would accelerate the nebula's accretion into a star. Gravity is dependent on mass and distance, and more mass in a smaller distance would mean gravity does its job all the merrier. Plus, the star would have more fuel to start nuclear fusion, and then, whoa, slow down! It's been too long, way too long since I've been in an observatory, and I don't see that changing anytime soon. Okay, so the proton area equals a neutron's area, and a proton equals not neutron. So proton bigger than electron, therefore neutron bigger electron. 8 proton, 8 neutron, 8 electron make atom 8. Dr. Akers, are you saying that you worked on your thesis for 4 years? That's thorough, to say the least. Nope. That was my PI's project. It was his research, his paper. I was the third author, which ain't bad. But, you know how research goes. And how's that? The little red hen bakes the cake, and then the PI eats it. Ooh, a visual. Transmission 256. Halfway to 1,000. Carrie, I think he's finally off his rocker. Should we tell Doppler? Settle down, let's hear him out. In base 8, the digits 400 are equal to 256. It is the halfway point to 512, which is the digits 100. Oh, we're doing this again. I hate base 8. Why must you keep bringing us back to those dark times? Embrace the aliens. Think like the aliens. Okay. So we have 3 particles. I'm assuming that they're illustrating to us what they are trying to define. So a proton equals sphere at 2. Neutron equals sphere at 1. Therefore, sphere at 0 equals electron. It's got a butt. Okay. So we are being shown something with 2 protons, 2 neutrons, and 2 electrons. So this is atom 2. Yay, a new word. Okay, it's a long message. Okay, so this unknown equals an atom. This unknown 1 equals atom 1. What is this saying? 8, 8, and 8. What element does this form? I've got a good guess. For the base 8 numbers, I'd guess the element is their favorite. It may be one of humanity's favorite elements, too. So, seems like we've already done that one, though, but... Okay, so let's see. We have unknown 1, comma, 1 equals atom 1. Unknown 1, comma, 1, neutron count equals 0. Unknown 1, comma, 2 equals atom 1. Unknown 1, comma, neutron count equals 1. Are they trying to define different isotopes? Try calling it an isotope. Isotope works. Good. I will turn off log now. Okay. So isotope 13 with a 27 neutron count equals 14. Isotope 13 with 27 equals atom 14? No? Okay. Okay, how are they using isotope previously? So they're saying this isotope 10, 22 equals atom 10. Isotope 10 is a 22 neutron. Oh, isotope 10, 22 equals atom 10 with a 22 neutron count. So this would be isotope 1327. Neutron count equals 14. So isotope 1327 equals atom 13. Okay, isotope 2356 equals atom 23. And isotope 1327 neutron count equals 14. Alan, I hope this isn't too forward, but I've been thinking about what you said. What you said about grad school, the research, being third author on that paper seems troubling to you. Maybe more than it should. And I'm no astronomer, but it sounds like an incredible paper. Something that you helped make possible. Shouldn't that be enough for you? Yeah, you're right. Journals love it, and it was highly cited. That's not what people care about. They wanted to meet my PI, the one man behind it all, ask him every question, and he'd have the answer. That's the thing. People just love to look for a face, a figurehead, someone to give all the credit, someone to accept the prestige. That's perhaps a troubling way to think, Alan. I know. I shouldn't even care about all that fluff, that recognition. I know it should be about knowing my own skills, my own impact, but I don't know. I just don't feel it sometimes. Okay, so for isotopes, we're defining first the atomic number and then the atomic mass, which or the number of protons and the neutrons put together. What have you drawn out for us here? Okay, so we have 2 hydrogen atoms. So isotope count equals 2. And then maybe we can say 2 atom 1? No? 2 atom 0? I don't think that's how we use this. So isotope count equals 2. Maybe molecule 0, atom 2, atom 1, isotope 1, 2? No, okay. Well, colleagues, do you have any ideas on formatting? Dr. Rose, I'm seeing 2 different units in this cluster. I imagine we have to name them properly. One consists of 1 proton and 0 neutrons, and the other consists of 1 proton and 1 neutron. Okay, let's see. How did they format isotope? Isotope. So we can do isotope 1, 1 and isotope 1, 2. Isotope 1, 1. Isotope 1, 2. This comma syntax is troublesome. Okay, that's correct, but we gotta have a better way to divide our commas then if we're gonna be doing stuff like that. Alan, if you're sitting in this room with Dr. Batista, Dr. Rose, and I, it means you're in good company. You're not here by mistake. People know your worth, the unique value you bring. Well, yes and no. People see that I'm good enough to get by, even on the Apollo program. I did what I could do to help. They had enough astronomers telling them the flight path to the moon was clear. So you ran for coffee. coffee, donuts, and whatever. Pretty robust background, ain't it? I would leave the first two off of any resumes. You say that now, but just wait to see how good I am at my coffee runs. Bautista, Akers, you guys. Let's see. Okay. Atom something has some number of protons, neutrons, and electrons. And I was asking which of these defines the atom, and the correct answer is the number of protons defines the number of the atomic, which atom it is. Alan, you are insightful. You must know that. We need you. Coffee? Bautista! No, we need you to decode this message. It's probably been 2 months since I last helped with anything. I hardly help solve these transmissions. I don't program a computer, and I don't do any linguistic analysis. But you start the discussion, Alan. You spark ideas. Even if you're wrong, you get us to think in a new way. I speak a lot, that's for certain. I suppose there's a minimal amount of help in there, though. I'd hardly call it expertise. Unknown. Okay, so we have an isotope with 1 and 4 unknown. 1 neutron, isotope 1, 3 add. Isotope 1, 3 unknown. So these equal each other. So isotope 1, 4 is equal to 1 neutron. Isotope 1, 3 add. Okay, so this is saying that if we take an isotope of 1, 4, this is equal to us adding 1 neutron to an isotope 1, 3. That makes sense. Whereas if we have isotope 1, 3 unknown, but I don't know what the unknown is defining, equals isotope 2, 3 add, we add an electron. And so the electron would cancel out a proton, bringing the atomic number down. Isotope 2, 6 unknown. This could be defining some sort of fusion or fission reaction? So this is adding an electron to do isotope 714. Because the electron will reduce the first number by 1. Don't know what that means, but I can work with the knowledge for now. Okay, so something are unknown equals 1 neutron, isotope 1, 3 add. So this would be isotope 1, 4. Alan, the hydrogen line. What? It's something you accomplished. You start the conversations. But if that's not enough, then I'd look to the hydrogen line. The very first transmission, the basis for every frequency we've received. I'm aware, if it weren't for you recognizing that specific frequency, would we be this far? We could have been stuck for weeks trying to do some meaning from those numbers. But you noticed the hydrogen line. You established our starting point. The aliens waved hello, and you were there to see it. I know, it's been my pride and joy for these past 4 months. That's it. I'm running out of fumes of achievement. Ratine, Alan, all of this is your achievement. The hydrogen line is my achievement. It's all I have to hang my hat on. You must know that there was a reason Doppler wanted you for this mission. You know the universe better than any of us. Okay, Akers, the pity party's getting a bit much. We know that you're a valuable member. Okay. Unknown equals proton recipe unknown. Electron recipe unknown equals this. So we have an unknown amount of protons and unknown electron recipe, and then unknown, I don't know, neutron recipe, it would complete the pattern. Okay, we're still using our same unknown, and we're saying that var3 equals var01 divided. And we're saying that 0.5 to the power of var3 multiplied by var2 equals var4. And if var0 equals 64, var1 equals 64, var2 equals 64, var4 equals what? So var0, var1 divided will be 1. So var3 equals 1. So 0.5 to the power of 1 is 0.5 times var2 is 32. Are we still doing chemistry? This feels like we moved on to a new group. Yes, we have. I have something to say. Many years ago, my older brother played in the Los Angeles Philharmonic. In the orchestra? That sounds quite prestigious. Mm-hmm. He even became the third chair percussionist, so he invited the whole family to his debut with the orchestra. The first percussionist was standing with a snare drum, a triangle, and an array of other instruments. My brother was sitting 2 chairs over. He remained sitting for most of the performance. I thought back. At age 8, my brother was playing Beethoven on the piano. Come high school, he was first chair percussionist in the school band. Each time he visited from college, he showed me a new instrument he had learned, and now he was third chair in the entire symphony. Yet he was sitting. Nearly 10 minutes had passed, and he had hardly played a single note. He hardly played at all that night. I'm sorry to hear that. Another passionate soul lost the crowd. That is how I thought, at first. Though after some thinking, I realized it was all the part asked of him. That's the point. It's a shame to waste that, to waste so much talent. Sounds like a brilliant performer. The symphony should have him play more. Maybe. Maybe. Would the songs have been better if he played more notes? That's very poignant, Bautista. Okay, var3 equals var0, var1 divided. Var, and then 0.5, var3 exponent, var2 multiplied. Suppose var3 equals 0. Then this would be 1. And then 1 times, so var2 equals var4. Therefore, var4 equals 1. Suppose var3 equals 1. Therefore, var4 equals 0.5. Suppose var3 equals 2. Therefore, var4 equals 0.25. And suppose, more supposing, continuing the pattern until we get var3 equals 8. 8 exponent. Therefore, var4, var equals var5. Statement var5, 0 equals something. Assuming that var5 is greater than 0, I don't know. var4 greater than 0? I mean, it would be true. Probably not what they're asking. Okay, var0, var1 divided. Crack open the whiteboard. Old friend we haven't seen in a bit. So v3 equals v0 divided by v1, and 0.5 to the power of v3 equals, or v2 times 0.5 to the power of v3 equals v4. And then, so if this is 3, then this is 1. Or this is 0, this would become 1 if r4 equals 1, which would make v2 equals 1. Then var3 equals 1. Then var4 equals 0.5. Suppose var3 equals 2. Therefore, var4 equals 0.25. So it keeps having. And suppose var3 equals 8 to the power of 8. Therefore, var4 equals var5. And assume var5 is greater than 0. Oh, this is asking if this is statement will ask us to evaluate if this is true or false. So this is true. This is the limit. Are we talking about limits? Let's define our new signal. Unknown. Okay, unknown b equals, sorry, saying var3 again equals var0 over var1. And again, v2 times 0.5 to the power of var3 equals var4. Now we say unknown b equals isotope unknown. var0. So that we have an unknown atomic number. Unknown b equals ... something. Okay, so we have a pass-through message here. X, Y, Z, unknown b. Another pass-through message. If they're saying X, Y, Z, unknown b, they're either getting ready to define some arguments or they want to define unknown b as position. Okay, so we still have var3 equals var0, var1 divided. These equations still hold. Isotope 2, 6, and then var1 equals var5. Isotope 11, 25, and then var1 equals var6. var6, var5 divided equals var7. var7 rounded to 3 significant figures. So we have v1 equals v5. And then we have v7 equals v6 divided by v5. And we want to round to 3 significant figures. So what's going on here? This could be a derivative. Oh, if we're getting into derivatives, I am not ready. Okay, what idea have they got? What is this? Different isotopes, each undergoing something. Hold on, let me check out the periodic table and the reference table. Why? What are you searching for? It's just a hunch for now. I found it. What is it? It's the half-lives. In the reference table, check out the periodic table. I think it's to do with the half-life data of certain elements. Oh my goodness, good find! So how do we respond? By comparing the half-lives of the isotopes. It is a ratio they are expecting. So we divide one by the other. Do it, Dr. Rose! Okay, so with isotope... Oh man, but someone could point that out because I would not have gotten that. So... Okay, this is isotope 2,6 bar 1. And this is... Looking at the isotope for element number 11. Salt. So the half-life is 59. Okay, isotope 3, sodium 25. The half-life is 59.1600 seconds. So when they mention the other isotope, helium-6, they say this is 0.8066 seconds. So they're saying var1 equals var5. Okay, I'm still a little confused on the formatting, Acres. If you could chime in one more time, be appreciated. Okay, equals var... Okay, wait, so they're saying this value here, they're putting into this. So var6 underscore var5 equals var7. So var7 equals these two. I understand. So we have 0.8066 and 14 point and 59.16. And we are dividing the first by the second. So 0.8066 divided by 59.16. If we round to 3 significant figures, that gives us 0.0136. Did I get it wrong? None of this working? Why? We're doing something wrong. Thanks, Captain Obvious. Hey, not conducive to problem solving. Okay. You have something? Divide the half-life of isotope 11, 25 by the half-life of isotope 2, 26. And that's all? Likely. Oh, did I just do it wrong? That would give 73.3. Okay, I did just have it backwards. Okay. So we have another pass through. So if unknown C equals unknown B, count 1. Oh no. What's wrong? It is a sad day. Bautista, you too, what's wrong? Signals -67 and -68. We skipped intriguing, but why sad? Unhappy dictionary, unhappy life. I forgot about you two and your bizarre rules. Okay, let's put in the pass through. Okay, so isotope 2, 6. And then it wants something defined. So we have one neutron separating. So this looks like we're going back now. I think I'm taking a quick break there, but I will be back in just a minute. And we're back from our short break. So let's look at what we're cooking up here. So we have a helium isotope, and it is a 4 neutron isotope, and we need to do something here. Now, what I was thinking before we took the break is that this might have to do with the fact that we are expelling one of our neutrons, which might be the definition of radioactive decay. I should probably read what that actually is. So let's see, if we look at chemistry, where would this be under? Chemical reactions, possibly? Decomposition? Oxidation? Not so much. Could it be under a different category? I wouldn't think so. Nope. Okay, Acres has a question. What are you saying, Acres? I've got a question. It's about something Duff was asking me after last meeting. Well, what is it, Acres? He asked me if I know any good burger places around here. I don't know of any myself. Oh, I was expecting something a little bit more relevant. I know, it's off topic and all, but do you guys know any good burger places? Unfortunately, I can't help you there. Hot patties. Oh yeah? They're good? Mm-hmm. I like their burger with onion rings. Awesome. We'll have to let Dop know. It's Bautista's probably got a catalog. I like to imagine that he's doing a little bit of a Michelin star tasting himself. Okay, so I remember something along the lines of us viewing a similar isotope chain before. So here we have these three, one decays. But which one had the previous transmission that also had a split off neutron? So it's going to be one with the colors, or the clusters. Here, perhaps 264? Yes, okay, here we have one split off. So this is similar to what we have now, but with a hydrogen, a hydrogen instead of the helium. So what was actually said in it? So we had isotope, 1 neutron, and our unknown. So this might be our decay is equal to 1 neutron. And so isotope 1, 3, add, we're adding the neutron, equals our cluster. So here we have the opposite. So perhaps this is isotope 2, 6, and then 1 neutron, subtract. Nope. Okay, did we have any ideas about what this could be? No, we did not. Okay. Let's keep looking at that previous transmission. So we have here isotope 1,3 add. Now, this means that we are adding this to this neutron. Now, here we are subtracting. Are we even subtracting 1? Because if we look at our current, that's 3 neutrons, 2 protons, and 2 electrons, and 1 neutron. So we're losing a neutron. What do we currently have undefined in our dictionary right now? We have 3 undefined terms here. Let's go ahead and try and come up with sub-definitions for these terms. So we know that in a transmission recently, we defined the ratio of half-lives rounded to a number of significant figures. So why don't we try and define this unknown as half-life? Now, we have a few other unknowns. So this unknown B, X, Y, Z, unknown B, perhaps this could define a point in 4-dimensional space. It could also define a speed. So unknown B equals var3, var0 over 1. And then exponent. So the isotope half-life var0 has an unknown B equals something something. And we answer 0 equals 0. So if this unknown B is equal to our isotope half-life, then maybe this is our radiation, and we're going to mark things that we're guessing with a G. This leaves one more that we haven't defined yet. Okay. So we're looking for our unknown C. Here. Our unknown C is equal to the radiation count. So this is the output of our radiation. So maybe this is like a gamma. This is a gamma ray or something. What is the term for a lone neutron? I guess it could be a neutrino? Okay. So isotope 2,6 something equals this cluster. Now, the previous ways that we've interacted with isotopes, the most recent one is here, where we have like 2,6 var1 equals var5. And perhaps we need to define the half-life rate of just isotope 2,6 because that ended up being what var1 was. I could see that. So in that case, if we look at our chemical periodic table and we look at our carbon 6 isotope, nope, we need our helium 6 isotope. Then we would say that the half-life is 0.8066 4-1. No, so they don't just want the isotope here. Unless we should assume that we're rounding to 3 sig figs? No. So then we don't treat this as just our pattern that creates the isotope. So we want to know about the actual decay chain. So with this being, I feel like we need to be able to communicate that one of the neutrons is leaving in some way. So knowing that, I want to go back to that transmission 264 where we talked about neutrons leaving. Because here we say one neutron, well, here we're talking about neutrons arriving. So we could say perhaps they're trying to affirm. Okay, so here they want to talk about the way that it was specifically decaying. They weren't looking for a numerical answer. Okay, so we're back to talking about what we think might be neutrinos. And we say that our var3 equals var0, var1 divided. And so we're back to this equation. I wish that it would tell us what this equation's significance is. Well, I don't wish it would tell us, I wish that I knew. I don't remember my calculus well enough, but I think that this might be a derivative. So or not the derivative, an integral. What is the integral of a constant number? Okay. Suppose that the radiation G equals 0 neutrino G. Suppose that our guess for radiation equals 0, and our neutrinos, our guess for neutrino and var2 equals 4096. Therefore, isotope 2, 6 counted equals 4096. Suppose that the radiation equals 1 and that our neutrino equals, or radiation equals 1 neutrino and something equals 4096. Therefore, isotope 2's count is 2048. Suppose that we have 2 neutrinos and something equals 4096, therefore our isotope 2 6 count equals. Okay, so we're changing the amount of output particles. And so when we have 0 output particles and then after this amount of time, after we have a starting amount of 4096, we end with a starting amount we end with a count of 4096. We double that, we get to 2048. So now here we have 2 neutrinos. So perhaps we're having it again to 1024. Okay. We are. That's not the most helpful. Okay. Uh, so we're talking about this ratio. We're defining a subject up at the top, and then we're talking about this second part of the equation, where we say v2 equals 0.5 to the power of v3. And no, v4 equals v2 times 0.5 to the power of v3. So our isotope 1125 with a var 1 equals 73.261. So does that line up with our knowledge of what sodium 25's is? Sodium 25 has a half-life of 59.16 seconds. So, not quite. What is this measuring though? Well, actually, no. This is the ratio to the half-life of uh, helium-6. If we go back to our calculator, no, okay, not quite. Although maybe depending on how specific these numbers were. So if we go back to our reference board, and this is, we add a 4-1 to the end. And we go back to our reference board for sodium. That's correct. Okay, no, not quite. Close enough that I feel like I'm onto something, though. Suppose the radiation G equals 0, neutrino G equals var2, and suppose and var2 equals 262,144. Therefore, isotope 1125 count is 262,144. Suppose that our radiation equals 144.522 or 146.522, which is double the half-life. So, wait, not radiation G, perhaps time? Time? Time, Dr. Rose? What do you mean? They mean time as a concept. Time. That which comes before and inevitably comes after. The independent variable of existence. The natural progression of matter in space. So they're saying at time. So suppose time equals 0. And the neutrino output and var2 equals 262,144. Therefore, isotope 11 25 count is 262,144. So now we have experienced 2 half-lives here. So we want 262,000 262,144, and we want to divide it by 4. And that gives us 65,536. No, no, not it. I feel like I'm barking up the right tree, though, because this is something that's beginning to make sense. Perhaps I am misunderstanding the equation, and we just need the 1. So if we divide these, 131,072. No, okay. It's not 131,072? I thought you were right on with that one, Dr. Rose. And me too. The duration of the transmission is twice that of the half-life of isotope 11, 25. Wait, it's twice the half-life? That means it'll cut it in half once more. Oh, I'm gonna take another quick break because my headphones ran out of batteries. And we're back. Sorry for the breaks this episode. Ugh. Okay, so I assumed that if it was twice the half-life, then this answer would be correct. The 65,536. This wasn't accepted. Oh, I guess I just made a typo the first time. Okay. Something half-life time equals neutrinos. Something half-life time equals neutrinos. So the amount of neutrino output something half-life time equals neutrinos. Do they want this equation? Do they want... What do they want? Suppose time equals 1. Right, they would consider 0.806614 to be 1 in terms of time units. So maybe they want atom? Isotope. I hate to lean on ideas this much, but you know, Dr. Akers gotta figure out what it makes sense. What do we put here? True? No, that would make 0 sense. You got a better idea? Yes, the transmission is illustrating the basis of neutrino G, right? I already know that. It's based on half-life time. Oh, wait. So they're defining a unit of time by a specific isotope. That's what they're looking for. Okay. Uh, so perhaps isotope 2, 6. I mean, probably that, right? Yes, okay. So then our transmission time, okay, I see. So this gives probably the transmission half-life time equals blank. So we can, that's not the neutrino G, that is the number of seconds. So we can change this to seconds. Hey look, it's transmission! Another old friend. I did not expect to see such linguistic sentimentality from you guys. What's transmission doing here anyway? The second! Well now... Oh, how do we know it's the same as our second? I'm not sure. Seems to be based off of isotope 2-6. I'll dig through the reference tab. Maybe something will pop up. It's not the same as our second. Probably worth noting. Okay. Transmission time equals transmission signal count. and second multiplied. Transmission 0 time equals 1 second. Transmission 1, 256 time equals 1 second. What was transmission 256? That doesn't sound right. Transmission 2 time equals 1 second. Transmission 3 time equals 1 second. Transmission 4 time. Okay, wait. Oh, they're not saying transmission 256. This was the content of that transmission. And they're saying how long they transmitted it for. So transmission 4's time okay, so transmission, right? So 3 numbers, 3 seconds. Transmission 5 time 4 numbers, 4 seconds. Okay, one of the signals that they were waiting on has come back. Okay, so something equals distance and time divided. I know what that is. That is our velocity. Actually, or speed. They might have something more to say about speed. I feel the need for speed. Yes. So time equals distance and speed divided, and distance equals speed and time multiplied. Speed equals distance and time divided. Time equals 0 seconds. So consider 0.00 and 0.80 that we move that 0.8 along the x plane, and the time equals 4 seconds. Therefore, the move time equals 4 seconds. Therefore, our speed equals 2, because we moved 8 in 4. Good stuff. That was a good week. Tough week, though, but a good one. Translation team, thanks for joining. Let's dive in. Get us started. Collins, Doppler, we're pretty excited. Oh? You remember the duration of each frequency? 0.80 something something seconds. 0.8066 seconds. We found the basis of said unit of time. Now, once again, chemistry, or physics rather, is beyond my expertise. Dr. Akers, could you summarize how it works for us? Happily. It's the half-life time of a specific isotope of helium, helium-6. It's their unit of time, their second. It's the basis for the transmissions, their frequencies. Goodness, it's been a long time since we've discussed the alien hertz, right? That was Baptista's clever way of tracking the difference in frequencies between each signal. And now you've got to the root of it. The half-life of helium. Helium-6, helium with 4 neutrons. Wait, 4 neutrons? That's way too heavy to be natural. They're artificially shoving neutrons into a helium atom, which is why half of it decays in 0.8066 seconds. It's horribly unstable. Why do they choose that as the basis of their unit of time? Unstable isotopes like that can't be found naturally since they decay before we've even observed them. They would have to have developed quite advanced nuclear science before settling on that as a time unit, which reinforces their perceived incredible technology. As we've demonstrated from their materials science, they're quite advanced. But why waste their time on a man-made or alien-made isotope? It's artificial. How could it predate the simple concept of measuring and dividing time by units? We do the same thing on Earth. Just a decade ago, we redefined the second. Based off of some complex nuclear thing with cesium. For what cause? So scientists all over the world could replicate the exact same unit of time. Human scientists needed to normalize the second to extreme precision. So we find a behavior of atoms that is exactly the same. Invariant of time or place. The unit is probably the same. A unit of time from far beyond their advanced science. But a unit that must be normalized for alien scientists all over the globe. And the method that they've chosen is a method that we can replicate even here on Earth. As creatures of the same universe, we can determine the exact duration of 1 second. 0.8066 seconds. Alright, that was a hefty week. 28 transmissions, 8 words, bringing us up to 67. And these are some interesting words. We're getting into some more particular physics, talking about some more advanced stuff. Maybe they'll start telling us how to advance our own material science. Sometimes all you can do is your roll. I'm finding my place. I must work on an important update. Alan will appreciate it. Dear Diary, why did the aliens design their messages this way? I ask this not to doubt their judgment, but for better understanding. Doppler's report. The employee of the week celebration has served us well. Started to boost morale and reward the translation team something a bit more simple and down to earth. Just a low stakes way to celebrate particularly helpful impact. It's about time this tradition has come to a close. Plus, I'm out of my kids' trophies to lend. I hope Akers gets his trophy. He deserves it. Alright, everyone's speculating about the words that we discovered this week. Alright, so thank you for watching another episode. If you enjoyed, don't forget to like and subscribe, and I will catch you in the next one.